Welcome. This is Dr. Sudha, Associate Professor, Department of Mathematics, Drupatunga University. In this session, let us look into the definition of stabilizers, orbit stabilizer theorem, as well as counting formula. To begin with, let us define what is a stabilizer. For that, we need a group which is acting on a set S. S is said to be G set here. Let us take an S in S. Then let us define what is stabilizer of the element S. And it is the set of all elements of G which fixes S. That is GS is equal to S, and it is denoted by stab of S, or we can even denote that as G suffix S. So G suffix S is the set of all elements which belongs to G which fixes S. That means S is mapped onto S. Now let us look into this lemma. Let us prove that GS, that is the stabilizer of the element S, is a subgroup of G. For that, we know that the identity element belongs to G. So E into S will be always equal to S. By group action, we have seen this. And this implies E belongs to G suffix S. Let us take two elements in GS and let us show that GS is closed. So let G1 and G2 belongs to GS. Since they belong to the stabilizer of S, G1S will be equal to S as well as G2S will be equal to S. So now let us consider G1, G2 of S. So using the second condition of group action, we can write this as G1 into G2S. So we get G1 into S because G2S is equal to S. And we know that G1S is also equal to S. Therefore, this implies that G1, G2 belongs to GS. Now, for every element G belong to GS, that is the stabilizer of S, let us show that it has an inverse in GS. So, GS is equal to S. So, let us operate with G inverse on both sides from the left side. So, you get G inverse of GS is equal to G inverse S. By taking the group action second condition, G inverse G will give you E, and E into S will be equal to S, and that is equal to G inverse S. So now we have the condition G inverse S is equal to S. Therefore, G inverse also fixes S. Therefore, G inverse belongs to the stabilizer GS. Therefore, GS satisfies the conditions of a subgroup. Therefore, it becomes a subgroup of G. Now let us look into this note. Therefore, we have two sets, that is orbit as well as a stabilizer of an element of a G set S. So given an action of G on S and an element S belongs to S, we have orbit of S as well as stabilizer of S. Orbit of S is denoted as O suffix S. Stabilizer of S is denoted as G suffix S. Orbit of S will contain elements of the form G into S, where S is an element which is fixed in S and G belongs to G. And this is a subset of S by group action. Next, G suffix S, that is stabilizer of S, will contain all those elements G belonging to G such that G fixes S, that is GS is equal to S. Definitely, this will be a subgroup of G. Now, let us state orbit stabilizer theorem and prove it. This theorem states like this: let G be a group and S be a set and G acts on S. That means S is a G set. Then there exists a bijection. Bijection means it is one and onto function phi from G by GS to OS. That is, G is a group, GS is a stabilizer, and this becomes a quotient group, and this quotient group is mapped on to the orbit of S. So where GS is the stabilizer of S, OS is the orbit of S. Also, this G by GS is the set of all left cosets of GS in G. Apart from showing that phi is a bijection function, we need to prove that cardinality of orbit of S is equal to cardinality of G divided by cardinality of stabilizer of S. So let us prove this. Phi from G by GS to GS can be defined as phi of G into GS. So this is a left coset because G is multiplied from left side. Let us map this to G into S. Definitely this will be an element of orbit OS. For all G belongs to G, we are defining this phi. Since we are defining this mapping, let us show that it is well defined. For that, let us take two elements are equal and let us show that their images are equal. So G into GS is equal to H into GS. So these two left cosets are equal. Therefore, the element G belongs to the left coset H into GS. Therefore, this G can be written as H into G dash for some G dash belonging to GS. Now let us operate by the element S from the right side. That is GS is equal to HG dash into S. And this can be written as H into G dash S using the second condition of group action. And this will be equal to H into S because G dash is an element in the stabilizer of S. Therefore, G dash fixes S. That is G dash S is equal to S. So GS is equal to HS. And this is nothing but phi of G into GS is equal to phi of H into GS. Therefore, phi is well defined. Now let us show that phi is 1, 1. For this, let us consider that the two images are equal. That is phi of G into GS is equal to phi of H into GS. And this gives us by definition of phi as GS is equal to HS. Now let us operate with H inverse on either side. So H inverse into GS will be equal to S because H inverse into H becomes E and E into S becomes S. And this in turn implies that H inverse G into S is equal to S. Therefore, this H inverse G is fixing the element S. Therefore, this must belong to the stabilizer GS. Therefore, H inverse G belongs to GS and this implies H inverse G of GS is equal to GS because this is an element of GS. Therefore, the left coset generated by this element H inverse G will give you back that stabilizer GS. Now operating with H on either side from the left side, you get G into GS is equal to H into GS. Here we took the images are equal and finally we prove that the elements are equal. Therefore, phi is 1, 1. Now let us show that phi is on 2. The codomain is OS. So OS will contain GS such that G belongs to G. And we have on the domain side that is G by GS. So phi of G into GS is equal to GS. So for all GS belonging to OS, there exists a G into GS in G by GS such that phi into G into GS will be equal to GS. Therefore, phi is on 2. So we have proved phi is well defined, phi is 1, 1 and phi is on 2. Therefore, phi becomes a bijection mapping, hence the theorem. But we need to prove that cardinality of OS is equal to cardinality of G divided by cardinality of GS. Since phi is a bijection mapping, the cardinality of the domain and the codomain are equal. Therefore, cardinality of G by GS is equal to cardinality of OS. if we assume that G is a finite set, we can make use of the Lagrange's theorem for finite sets. Therefore, cardinality of G by Gs is nothing but index of Gs in G. So that will give you cardinality of G by cardinality of Gs. That is order of G divided by order of Gs. So when we substitute this value on the left hand side of this, so we are going to get after cross multiplication, that is order of Gs into index of G into Gs is equal to G. So we get order of Gs into order of OS is equal to order of G, because we have index of Gs in G is equal to cardinality of OS, because phi is a bijective mapping. And this expression is known as counting formula. That is, the number of elements in an orbit must divide cardinality of G. Likewise, we can say that the number of elements in GS will also divide cardinality of G. Thank you.